So we will go ahead and get started. Want to apologize for the miscommunication on project one. We're going to start by going over that. I've been talking to Kevin and Mariah a lot today, trying to clear things up. We are doing the same project one as the majors. We will do different projects 2 and 3, but project one is the same. We will have everything out there. As of now, we're going to make that due Monday, the 12th of April. Given the late start, if I have to give an extension, I will. I'd rather not for a couple of reasons, but for now, it's going to be due Monday, the 12th, which is Monday in 2 weeks. It should be enough to do it. Like I said, we're going to talk about it now. We'll talk about it in class, and I know Kevin and Mariah are both going to have sessions to discuss project one as well. One of the reasons for wishing to not delay the due date is that an exam number 2 is 2 weeks from today. That is Wednesday, the 14th of April. As with exam 1, it's during the class time on Blackboard. It will look about the same. It will have about the same number and type of questions: true, false, multiple choice, short answer, and programming. Today, we're going to do a little bit more about dictionaries, and we're going to talk about mutability, different types and how they work in Python. And then next week, we have both lectures currently scheduled to be on recursion, and the test will be cumulative up through everything in recursion. I mean, it pretty much has to be cumulative because you're not allowed to forget how a while loop works or what an integer variable is or anything like that. But it'll emphasize the new stuff. There'll be sample exam and everything else, same as last time. What I do want to do is spend the first part of class then going over project one. Now, the assignment is to write a Python program that simulates the game Mancala, or Mancala. I've always pronounced it Mancala. We've given you a starter program to use, and I'll talk about that. But first, I want to explain what this game is all about and how it works and what you're going to be doing. So here's a YouTube video. A Mancala board consists of 14 what are called cups. 12 regular cups, the 6 in the top row, 1, 2, 3, 4, 5, 6, and then 6 in the bottom row, and then 2 bigger cups at the end. These 2 bigger cups are called Mancalas. You have 48 pieces, stones, balls, whatever. They're called stones generally. And you start with 4 of the rocks, 4 of the stones in each of the normal cups. Nothing in the 2 Mancalas, but you put 4 stones in each cup. When you play the game, you have presumably 2 players. Each of them takes turns. And what you do is when it's your turn, you arbitrarily, well, not arbitrarily, strategically, you pick one of the cups, take all the stones out of that, and put them in each cup in order, 1 per cup as you move along, which he will start doing in just a minute. He's explaining this. I've muted the sound because it doesn't come across very well. But again, you've got these 12 cups, and you've got 4 stones in each cup for a total of 48. There's actually a number of different rules. I'm going to explain one thing once he starts moving them in this. This is only a 3-minute video, so we've got plenty of time for this. So he's picked that cup from his strategy, and he's going to take each stone and put it 1 per empty cup. Now, what I want to stop the video for just a second. He went counterclockwise from our view, from the camera's view. He went counterclockwise. In your program, you're going to go clockwise, but other than that, exactly the same strategy. He put there were 4 stones in this cup. He put 1 here, 1 in the Mancala, 1 here, and 1 here. So that's what he did with the 4 stones. He put 1 in each cup. Okay, now that turn is over. And now it would be the other player's turn, and you can pick, again, from a strategic standpoint, you could pick a cup and put one stone in each cup and move along. Okay. He is, just for demonstration purposes, always starting wherever he finished. You don't have to do that. The player can pick wherever he wants to start from and lay these out. So you're just putting these things in. The game ends. This is a one-person game, which is why he's not using the other Mancala. The game ends when one of the two rows, either top or bottom, is completely empty. You can never choose the Mancala, the piece at the end that he's pointing at. You can never choose that to start. Once a stone is in there, it's done, and that's it. And as I said, the game continues. Now he's no longer picking the place where picking the place where he stopped. He's just going on. The game ends when either all the cups on the top or all the cups on the bottom are empty, and the stones are either in one row or in the two Mancalas. That's the game, and I'm going to stop the clip now because it just walks through. That's the game you're asked to simulate. Okay, and so you are going to write Python code that will simulate this game. Now, in the instructions, it mentions right here that there is a starter file which you should download to start the program. So I've already downloaded it. I've got it on PyCharm, and what I want to do right now is show you what it looks like. When you download that file, you'll see that it contains a bunch of code. This is the starter.py file, and you'll replace this initial comment block with your standard header. Your name, your section, this is project 1, this is spring 2021, the date, and all the standard comment stuff that you have. These next few lines are constant definitions, which you will find you'll use in your program. Okay. Now we've given you, actually Professor Hamilton wrote this. This is Hamilton code. A set of, functions that you can use. Don't change these, just understand how to use them. So draw board draws the Mancala board on the screen. It will draw something that looks like what you saw on that video, with the top cups and the bottom cups and the Mancalas on the two ends. Okay, this is going to draw a board. There's admittedly, it is cheap, lousy ASCII graphics. If you've heard that term, it's not going to look beautiful or elegant, but it'll get the job done. This is what you should use to draw the board on the screen. So again, this is code for you to use. Just don't change it. Just use it. I'm not going to go through it right now. If you want to play around with it and look at it, that's fine. But wait until later. That just is a function we've given you to draw the board on the screen. The next two functions are helper functions. The next three functions, actually, are helper functions that, again, are provided. Draw Mancala and draw block are things that just help draw that board on the screen. Now we come to the functions that you have to write. In the instructions, it says you have to write a function called getPlayer. GetPlayer is just something that you write that asks the user to type in the names of the players. So this is a standard function you've written before. Get the name of the player and pass them in. Now, this word pass, I don't know that we ever talked about it when we were talking about functions. Pass is essentially a no-op. What you do is you put pass there to say, I am going to write a function. I have not written the function yet. It does nothing, but it lets me test the code. Okay. It lets me test the codes that I've written so far without causing any problems. So pass is something that's eventually going to be replaced when you write the code. You're going to write the code for getPlayer, and what it's going to do is it's going to prompt the user for the player names of the two players. It's going to type them. You're going to type them in. It's going to read them, and it's going to pass them back to the main program. You're going to write this function, run game, is going to actually execute the code to do all the things that we're going to talk about here. And then take turn is what happens during one player's turn. Okay. So your main program in its entirety is right here, and you don't modify the main program at all. All main program does is it calls run game. Run game, when the code is written, is going to execute the code needed to simulate the game. Right now, again, pass does nothing. It's just there. Okay. And it calls take turn when it's player one turn. So player one turn, and what cups is available to player one, players two turn, and so on. So run game is going to call take turn in order when the player's turn and the other player's turn. So you'll call take turn with player one, then you'll call take turn with player two, then you'll call take turn with player one again, and so on until the game is over. So your task is to write these three functions: run game, take turn, and get player. This, as I said, this file, starter.py, is what we tell you to download in the in the instructions. That's what you're going to download from Professor Hamilton's public files. If you run it right now, it should run, but it does nothing. You can see it doesn't accomplish anything because run game is an empty function. It's not there. But that will make sure that you downloaded the correct file and nothing is incorrect. So this file right here that I'm highlighting on the screen, when you download that file and have it, that's what it will look like. It has that code. It talks in here. There are functions in the file as well as some constants, the constants you've seen. The three functions in the file: draw board is what you call to draw the board. The other two functions, draw mancala and draw block, just says those are there to help draw the board. You don't do anything with them. You just leave them alone, and it's probably there. And as Professor Hamilton says, we're not really providing any documentation because we'd like you for this assignment to just leave them alone. Just use those functions, use that code that's been given, don't mess with it. The real assignment is to write the functions run game, get player, and take turn, and write any other functions you need. Now, we tell you arbitrarily you need to include at least two more functions. Your choice. You're designing the software, you're writing the program, you're going to do this. It really is easy to come up with other functions when you think about it. I mean, Hamilton and his internal solution that we kicked around as faculty and talked about has 5 more functions. You're not going to have any problem having 2 at least. But at any rate, run game sets up the board, alternates between players, and determines the winner at the end. You do not want a 100-line function here. It doesn't take that. It shouldn't be more than maybe 15, 20 lines of code in this function. Get player is fairly straightforward. As we said, this is a function you're used to right now. Get the players' names. Ask the user to type in the players' names. Player 1 is Joe. Player 2 is Kamala. We're done, right? Player 1 is Larry. Player 2 is Boyd. That's the governor, lieutenant governor. We're done, right? You ask the user for the 2 names. You read in the 2 names. You return the list of 2 names. That's a straightforward function. Take turn. You can change it if you want to. What this function does is it prints the board. Okay. That using the functions we've given you, it prints the board. It asks for the new move. The user has to type in, okay, it's Joe's move. Joe says, I want to start at cup number 3. You have to verify that it's a legal move. You have to verify the input to make sure it's real. Okay, I'll explain what the legal cup numbers are in a minute. And then you make the move. And there's some special rules that we can go through Monday to make sure you're far enough along. Step 4 in here says, is what I just said verbally, You have to create at least 2 more functions to help you finish the project. You can't hand it in with just the functions defined here because that's not good design. You need to define a couple more functions and write them. That's fairly easy, fairly straightforward. You can do that without trouble. You know, it can be 4 or 5. It's not a big deal. We can do that. Okay. Coding standards tells you what to use. It's the standard thing, what you can't use. Let's see. You can use dictionaries if you want. I don't think you need them. I didn't need them in my solution, but you can probably use them if you want to. Don't use things we have not covered in class. Don't use any of these built-in functions. You shouldn't need them. This is not a big problem. When you run the program, when you draw the board, looks like this. It gives you this. This is the output right here of draw the board. Okay. This is the function here. These first 2 lines, these are the function of get names. That's all get name does. Player 1, what's the name? Player 2, what's the name? Read them in, return them. That's all function get names. The draw board function, this is what it's going to do when it prints out the name. Okay, it's going to tell you it's going to tell you that this is Boris's Mancala and this is Abby's Mancala, and initially they have 0 stones. You start the game with nothing in the Mancala. You start the game with 4 stones in each cup, and this is what's going to be printed out. This next line is a result of take turn. It says player, it's Abby's turn. We start with player 1, Abby starts. What cup do you want to move? Cup 1. Cup 1 has 4 stones in it. Take all 4 stones out of cup 1. It now has 0. And go clockwise, distribute them. Now, as I said, the video I showed to start this lecture said, yeah, we did go counterclockwise. It's not a problem. Go clockwise, move up in numbers. Here's the deal. We go clockwise. That says go from 1 to 2 to 3 to 4 and to 5. Okay. If we were going counterclockwise, we would start and go down. We would start at 5 and go 1 and 4, 1 and 3, 1 and 2, 1 and 1. To distribute a stone, just add, you have the number of stones in each cup. To take these 4 stones out of cup 1, you take 4 stones out of cup 1. There's now 0 stones in that cup. And add 1 stone per cup until you run out. Plus equals 1, plus equals 1, plus equals 1, plus equals 1, right? Add 1 stone to each of those 4. Now those 4 stones we distributed are gone. And now the board looks like this. Now it's Boris's turn. Boris says, I'm going to pick cup 2. Cup 2 has 5 stones. Set cup 2 to 0. Add 1 becomes 6. Add 1 becomes 6. Add 1 becomes 6. Add 1 becomes 6. And add 1 to the Mancala, and this becomes 1. I'm sorry, this gives 5 and 1. Right. Okay. Now, there's a special rule in the instructions. The last stone was placed in this Mancala. The last stone went here. So it's Boris's turn again. That's the one time you don't switch turns automatically. The last stone went here. Okay. So you ask Boris for what cup does Boris want. Boris says, I'm going to start at cup 3. Cup 3 has 6 stones. 1 here, 1 here, 1 here, 1 here, 1 here, and 1 here. And now it's Abby's turns. Okay, this is what the board looks like here. Going clockwise, Boris's Mancala is cup 0, Abby's is cup 7, and so we go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and the last one is cup 13. So as you're going, just increment, right? Go up one cup, add one to the number of stones, go up another cup, add one to the number of stones, and so on. Okay. Abby's turn, Boris's turn, Abby's turn, go again, and so on. Now, when either the top row or the bottom row is completely out of stones, look, the top row is out of stones. What you're doing is you're checking to see is cup 1, 2, 3, 4, 5, and 6 all equal to 0. That means the top row is out of stones. Or is cup 8, 9, 10, 11, 12, 13 all equal to 0? That means the bottom is out of stones. When that happens, the game's over. You figure out who won. Abby has 5 stones. Boris has 1. Abby wins. Okay. So run the game, controls this whole thing. Player turn handles the notion of taking all the stones out of a specific cup and redistributing 1, 1, 1, 1, and so on. And then you draw the new board. And then you just have to have a quick check. Here's a hint. Draw a new function to determine who's the winner, right? Write a new function to determine who's the winner. You don't have to, but it's a whole lot easier if you do that. And then you can print out this message. Okay. We will put out a version, a compiled version, no fair decompiling it, reverse engineering it. So you can play a game and see what the sample output should be again. You don't have to match the messages exactly, but the flow should be. Okay. So if you look at this program right here, it's PYC, means it's compiled. You can actually run that, copy that, and run it on GL, and it will, you can test your output to make sure you're working correctly. Okay. So that's the background. Notion, if you try to copy this executable file, this compiled file, the PyCharm, it probably won't work. It might, if you can make it work, great, but we only guarantee it works on GL. Run it on GL. The whole point of that, again, is to make sure that you get the right answers, that your program's working, that you understand what you're supposed to do. So that, in 22 minutes, is project 1. It's out on the system. It's in the announce. If you haven't seen it, you can fetch it from Discord, from the class Google Drive. Again, don't worry about Friday the 9th. That's for the major sections. For us, it's Monday the 12th at midnight, because we did get a late start on this because of communication breakdowns between me and the TAs, which are completely my fault. Do not hold Kevin and Mariah for this one. This is me. We didn't have a clear. We didn't have. They and I were not on the same page, and that's my fault as professor. So we'll get this done. You have until Monday the 12th. If I absolutely have to give extensions, I will. But please try to get it done before then, because program 2 will be coming up rapidly. More importantly, exam 2 is that Wednesday the 14th. I'd like you to be able to focus on studying for the exam rather than get project 1 done. But it will work. That's a background on the game. That's a background on the starter file we give you. Please make sure by Monday, the 5th of April, which is next Monday's class, I want to do a quick check. I want everybody to let me know by Monday's class on the 5th that you have been able to download that file, to copy that file with the starter code in it, and make sure it runs, at least does not have errors, even if it doesn't give you anything, and that you started on the project. If you have not started on the project, if you have not been able to download that file by Monday the 5th, then there's probably going to be an issue. We need to get on it real quick. I'd like to stay on top of this again, especially because it's your first major program in this class, and especially because we got a late start. So I'm gonna heckle you all on Monday, next Monday the 5th, when we start recursion. We will spend another 15, 20 minutes in that class on Monday talking about the project, but I want to make sure that all of you have been able to successfully copy the starter program file and gotten to work on some of it. I understand you're taking other classes, understand you've got other work going on, and I also understand this weekend is Easter, and for some people that's a big issue, and the Passover is going on, and for other people that's a big issue, and I completely support that. But I'm going to check to make sure that by Monday you've at least got started on this, because I really don't want to have somebody come up on Sunday the 11th and tell me, I can't copy that starter file. What do I do? Okay. If you have problems copying it, that's legit. Understand people have problems with GL. If you have problems copying it, I'd like to know now. If necessary, I can put a copy of it on the GitHub. I can put a copy on Blackboard. I can put a copy someplace else. Let's get you started. That is project 1. Okay. Again, Kevin and Mariah both are planning sessions on that project. The next time they're on Discord, so let's jump ahead of this, folks. Let's get out there and get it early. With that, there were a couple of things I did not quite get done on Monday. I want to skip 2 slides ahead and talk about keys and values. Now, this is something I sort of talked about on Monday. On Monday. I had my dictionary, and I'm going to try to replicate it, but roughly I had the list of my dogs that I've recently had. And Doug he's got the list of a beagle and a bulldog. And what did I do wrong to get that typo? Hang on. I've got the wrong kind of a quote there, I think. I'm missing the close quote after beagle. That's what PyCharm is trying to tell me. I had Lizzie. I'm just going to call her an ACD. She's an Australian cattle dog. We're going to abbreviate that ACD. I had Bonnie. Bonnie was a beagle. And I had Penny. And Penny was a Cocker Spaniel. And let me make sure that I haven't messed any of this up. It looks to be correct. Okay. So let's run this in a console. Okay, now there are 2 methods that I can use that are built into Python to manipulate dictionaries. And one of them I used on Monday, but I didn't bother explaining it. So now I want to go back and explain it. And that is keys and values. If I say dogs.keys, what will happen is Python will put together a structure, an object containing all the keys in my dictionary. So remember, the keys are the things to the left of the colons. It's the main entries, the indices in my dictionary, the whatever you want to call them. So the keys are Doug, Lizzie, Bonnie, and Penny, the names of my dogs. If you ask for dogs.keys, it will bring back a structure containing all the keys in the dictionary. Now, what this means when I print it out is it is not a structure you know about. It is not a list. It is not a dictionary. It's what's called a view object. Okay. So what we have to do is understand that we cannot use the keys method directly for some things. We can use it for others. I can, for example, use, and this is the example, this is what I did on Monday. I can say for key in dogs.keys. And this is a for each loop. If dogs.key equals Bonnie, sorry, print dogs.key. Now, this is not going to give me a match. It's going to work, but it's not going to do anything. Oops. Okay. Yeah, that's the wrong code. What did I do on Monday? Hang on. What did I do on Monday? Yeah, never mind. I'll figure it out. The point is, you can run through all of the dogs.keys, this structure, and it will check to see if you have a match. Let's fix this. It's not dogs.key, it's dogs of key. It's dogs square bracket of key. There we go. And I'm going to change it to Beagle. And this is the example that I used on Monday. All right. Okay. That's what I want. Okay, that's what I want. Debugging software is so much fun. Okay. Okay. So what I want is for key in dogs keys. Okay. So now I'm going to go through Doug, Lizzie, Bonnie, Penny. And I'm going to take about one more second on that because we get a lot of stuff to talk about, and I'll figure it out. There we go. Okay. Basically, that got it figured out. Basically, what I do is it lets me cycle through all the values in that are keys in my dictionary and do something with them in this case. But I cannot directly do something with this dogs.keys because it's not a list. It's a special object. But I can use it to go through and find a key and work like that. Similarly, there's values. So dogs.values goes through the values of my dictionary and creates a view object, a special object consists of all of them. And so you can see that it creates an object of type dictionary values, and that will contain Beagle Bulldog, which is Doug, Australian Cattle, which is Lizzie, Beagle, which is Bonnie, and Cocker Spaniel, which is Penny. The point of this is that you can use keys and values to search the values, to search the keys, to search the list of keys in the dictionary, and to search the list of values in the dictionary looking for a match. And that was actually what I did on Monday when I gave the illustration of how do I find out, how do I look for which dog is a beagle? How do I search for a value? And the answer is you cannot directly search for a value. What you have to do is use all of the values, go through this object, and then see if you can find a key that matches, okay, which is what I did. I went through on Monday, I went through all the keys, looking at the value associated with each one, and I found the key that matched the value I wanted. I could have also gone through the list of values, determined that the value I wanted was in there or not, and then taken some other action. The point of this slide is you can create objects consisting of all the keys and all the values, which you can use for other things. And then the last thing about dictionary is Python will let you build a dictionary from two lists. There is a constructor method called dict, which just create a dictionary, and there is a defined function called zip. The short version of this is here on the left. I have two lists. And then I use the constructor build the dictionary and the Python function zip, and I build it, and it looks like and let me fix my indentation. And this is going to be my result, so I don't need that. And now we will execute this. This is a useful tool if you're trying to build a dictionary out of something else. So what I do with zip is I have two lists. In this case, I just called them A and B, and they have 3 elements each. A is 1, 2, 3, B is 4, 5, 6. What zip does is it says start with the first element here, pair it with the first element here. This is the key, this is the value. The first list is going to be the list of keys, the second list is going to be the list of values, and it zips them together. This, kind of like a zipper closing up where you have a tooth from each side falling neatly into order. So zip builds them. However, zip by itself does not produce a useful object. It's not a list, it's not a dictionary. In order to create that, so if I just said A is the list of 1, 2, 3, B is the list of 4, 5, and 6, and now I say zip A and B, I get, again, a zip object. I don't get a list, I don't get a dictionary, I don't get anything useful. I have to say, take the output of zip of A and B and create a dictionary from it, and that's how I get this. So you can build a dictionary this way. It's a constructor method. Now, in this example, everything is the same length. What happens if they're not? Let me change A. So A is now going to be 1, 2, 3, A, B, C. No, let me not get into strings. Let me make them 8, 9, and 10. And now we'll create a dictionary from zip of A and B. And it just matches up key value, key value, key value. If one is longer than the other, if one list is longer than the other, it continues and adds in the values, the elements from this list. but these are the keys, and there are no values to match up. Okay. Okay, and you weave through. When I say a zip item in the text of the slide, I said that's an iterator. Dict is a constructor that turns it into a dictionary. Again, if you just say zip of A and B, you don't have anything useful. You actually have an intermediate thing. You have a zip object, and then matches up. Okay. If one list is longer than the other, it actually does append things, but there's no matching of keys and values. So there's nothing meaningful in a dictionary, which is why you didn't see it. All right, so that is the rest of dictionaries that I didn't get to on Monday. We've now covered that. The rest of today's lecture, I've got a little over half an hour, is the topic of mutability. And this is where I admit that I've been lying to you for all semester. And I sort of hinted I have about how Python works internally. It turns out I've been telling the truth about some things, but not about others. Here is in one, and you'll see the slide again at the end. Here is in one slide what you need to take away from this lecture. If you take this material on this slide away from this lecture, you're going to be good. The term mutable means it can be changed after it's created. Okay, you can create it and then you can change it. That means mutable. It can mutate. It can become a new coronavirus. It can become something different. It can change. Immutable means after you create it, that's what it is, and it can never be changed. Now, here's where I've been lying to you. In Python, simple types like ints, floats, booleans, and strings are immutable. They cannot be changed. Wait a minute, Arsenal. What are you saying here? Okay, let's cover that in a second. Complex types, lists and dictionaries are mutable. Let's explain what I mean and give some examples. There is, I'm going to come down with some new variables, a equals 5. Okay. There is a function in Python called ID that will tell me the address of a variable. So what is the ID of A? What is the address? What location in memory is A at right now? A equals 5, and on my Mac, with the software I have running on my Mac, with everything else going on, this is the address. This is the location in memory where A is stored. That's what the symbol table does. The symbol table tells me A is in that location in memory. Now, come on, for crying out loud, all semester, we've said A plus equals 1. And A now has the value 6. How can I pretend that A can't be changed after creating when I just added 1 to it? I changed 5 to 6. I just changed it. How can I say A wasn't changed? For the following reason. Here is the location in memory A was. After we added 1, look, A is at a different location in memory. A used to be here. A is now here. Okay. Let's understand this. This is an important part. I changed the value by adding 1 to an integer, but I didn't really change the original variable that was immutable. I didn't change the original integer because what really happened is Python destroyed the old location in memory and created a new one. So if it's an integer, what happened is the symbol table says here is a location in memory and here is where A is stored, and A has the value 1. That was that, or 5, or whatever. That was that first location in memory I showed you using ID. Okay. Now, when I executed this statement, a plus equals 1, simple change to the value of a, what Python did is it said, this is gone. This is now garbage. This location in memory has bits, but it's not bits that are meaningful to me. Let's get a new location in memory, and 1 plus 1 is 2, so let's store the value of 2 there. And the symbol table is actually updated. So anytime you have a simple, immutable variable, an integer, a string, a float, a Boolean, anytime you change it, the way Python works is it destroys the old location in memory, deletes it from the symbol table, doesn't physically go in and demagnetize things, but it erases it from the symbol table, and it creates a new location in memory, and it stores whatever value is calculated in that new location in memory. So for any immutable variable, int, float, string, Boolean, Python gets the value, puts it into a new location, and these are now a before this statement and a after this statement are now different locations in memory. This is gone. Okay. That is an example of an immutable variable. This is why we cannot change a string. Okay, remember I said if you've got a string, you cannot replace one letter in a string because a string is immutable. What you would have to do is go in and copy the string over letter by letter, replacing the one that you want to change, and then storing the new value in a new location in memory. And we do that by using lists. That is an immutable value. Okay. Anytime you change an integer, certainly you can run an a equals a plus 1, right? A plus equals 1, a equals a plus 1. Certainly you can do that. That's a fundamental part of Python. What happens when you do that is it destroys the old location in memory. It creates a new location in memory with this new value. Okay. For types that are complex, they're built out of other types. And for what we've covered in this class, we are talking lists and dictionary. Lists and dictionaries. Those are mutable. Those can be changed. And so that is why you can go into a list and you can change the value of a list, of an element of a list. It keeps everything in memory in the same place. Nothing changes. Nothing changes in the symbol table in memory. That's why you change the value of a list. So a mutable variable, like a list or a dictionary, you can keep the same location in memory, and you can change a value in simple variables like strings and integers. When you change the value, it throws away the old location in memory, and it puts the new value in a new location in memory because it's an immutable variable. Now, that's adding 1. There are stranger things that appear when you do a copy. Okay, so for example here, we're going to take these simple integer variables, and this is going to behave exactly like you think it should. Okay, set a to 1, set b to a, add 1 to b, and print a. Well, a was 1, then b was 1, now b is 2, print a. A should still be 1. Hey, how about this? This actually works. Nothing up my sleeve. B is actually 2. Why? Immutable variables, when you copy them, you just make a copy of the value and put it in a different location in memory. So this was my original A. A was 1. B also became 1, but it got a different location in memory. So B and A were different locations in memory. Then when I added 1 to B, it became 2. I threw away the original value of B, the original location, and stored the new value in this new location. And so now I have B with 2. That's why that code worked exactly the way you expected, because those are different locations in memory. So when I added 1 to B, I did not change A. That's everything you expect it to be. But here is going to be a change, because lists are mutable. This is going to be where we talk about strange behavior in Python if you don't know what to expect. C is a list of integers, 1, 2, 3, 4. D equals C, so D is a list of integers, 1, 2, 3, 4. Append 5 to D, the integer 5 to D, print C. Now, I haven't changed C. Nowhere did I say set C equal to something else. Nowhere did I add anything to C. I'm going to print C, and what's going to happen? C has been changed. When I appended a value to D, it also changed C. Why did it do that? Because lists are mutable, and mutable variables behave differently. Not only when I add things to them, but when I copy them. Okay. Over here, when you have a list or a dictionary in Python, and you assign something, so C was 1, 2, originally it was 1, 2, 3, 4. C had this location in memory. When I set D equals C, the simple statement that D equals C, make that a small d. What that did, D equals C, caused D and C now to be pointing to the same location in memory. I did not make a copy of C and put it somewhere else. With an immutable variable, with an integer, a string, a Boolean, or a float, when I have this assignment statement, B equals A, I make a copy of the value, I put it in a different location in memory, I'm pointing to different locations in memory. With a list or a dictionary, when I have an assignment, D equals C, I'm not getting a new location in memory. I'm not making a copy. I'm just pointing to the same location in memory. And so because of that, when I changed D with this statement, I also changed C, even if I did not intend to. So the implication of having mutable variables is you can change them in unexpected ways. You can change them in ways you didn't want to and you didn't think you were, because of the way Python handles memory locations in the symbol table. Let's go back to our case here. What is the location in memory of C? C was that list. It's this thing. What is the location in memory of D? Lo and behold, D and C are the same location in memory. So anytime you have a list or a dictionary and you have an assignment statement, it's the same location in memory. You're not going to change it. And therefore, changes in one will be reflected in the other. Whereas up here, A equals 1, B equals A, ID of A is this, ID of B is that. That's not supposed to be pointing to the same location in memory. It's an integer. Okay. But it makes the copy. I'll fix that one. Okay. So, immutable, cannot be changed after being created for any reason A equals A plus 1, you get a new location in memory, and it's technically a new variable. It's a whole new object and with a new identity, and the previous one is destroyed. We don't physically demagnetize it. What it does is it deletes the value from the symbol table and puts the new value in. Mutable can be changed after being created. Appending a value to a list mutates the list, inserting, popping, removing, what have you. But if you make a new assignment, that's a new list object. Let's go back and say, what do I mean by that? C equals the list 1, 2, 3, 4. That location in memory. Okay, we already know that D equals C. That's the same. But if I now say C equals just the value 2, 3, 4, I manually remove the value 1, and now I do IDC, that is a different location in memory. So that's what that bullet point on that slide means. When I make a new assignment, this is a whole new assignment of the variable C. That is not an append, that is not a pop, that is not a delete, that is not a remove, that is not anything. This is an entirely new assignment. Now I get a new location in memory. That's going to be important for managing copies of lists. Okay. The Python symbol table, this just summarizes what I've said. The symbol is the variable. It says it's an integer, and here's where it is in memory. This is a string. Here's where it is in memory. This is a function. Here's where it is in memory, and so on. ID, the ID function just goes into this, takes the symbol and returns this value, where in memory it is. Okay, and so that's why we went through and used ID. It gets the address. In general, using ID in this class is very limited. When you get into some serious hardcore programming, it's important to know the addresses. But please, for 201, don't use ID other than to illustrate to yourself how it works. It's not a fundamental part of programming in this class. But we can use it to illustrate mutability. These are some examples I've already worked through because I'm running kind of low on time. I'm not going to go through them again. You can do that. The one I will illustrate is this, and I'll have to fix my typing. Everything, it just shows you everything I've done before. Here, this is a small x, not a big X, or it's not going to match. Okay. When I run this, I'm missing a parentheses. That's why it's not working. Okay, why is that a syntax? There we go. What happened? This is 1 for I in range 10, x plus equals 1, print the ID. Okay. Every single time I added 1, I got a new location in memory. Every single time I printed X's address in memory, it was different. Every single time in that loop, every single location in memory was different. Now, if you are interested, we can have a talk sometime later, not in class. It went up by 32 every time. That's a function of the way Macintosh handles Python. It doesn't matter. On different computers, it's probably going to be different. It's how long each part of memory is. These are always 32 apart. The point that you pay attention to is, in that case, I just ran a loop and I incremented X every time by 1. And every time I got a new location in memory. I mean, which seems like it ought to really be a waste. Why would you do that? Well, there are actually some reasons you would do that. I'm going to come back to this in a minute. This is the illustration, my lousy graphics, of what's happening in memory. This was the slide I wanted to get to. Why would you do this? No, this is not on the test. In 2 weeks, you will never see this on an exam. It is not fair to ask you this. It's an illustration, okay? The real answer is because the guy who invented Python, a guy by the name of Guido van Rossum, who's Belgian, wanted to do it that way. Why? Because in reality, immutable objects are faster to access when the program's running. It is faster for the program to access an integer, a string, a whatever, than it is to access a list or a dictionary, a mutable object. And so by having strings and integers, etc., be immutable, it speeds up the performance of your program. It makes it run faster. Okay. When you have to create a copy to change them, it turns out that lots and lots, when you know, this is data science again, right? When you analyze millions and millions of different programs, it turns out that lots and lots of coding involves objects that never actually change. Lots of strings are defined and they never change in a program. Lots of integer variables get a value and they never change. Lots and lots of times that happens in code. So therefore, you get better overall performance. Your Python programs will run faster when you make strings, ints, and floats immutable. You make them unchangeable, except for this way we've talked about. We're creating a new one. That makes your programs work the best. Lists and dictionaries that are complex, it turns out they almost always change. Almost nobody, almost never do you define a list and then never change it in your program. Almost never do you define a dictionary and never change it in the program. It does happen, but in the corpus of all the computer science programming, it's very, very rare. So therefore, it's easier and faster to make lists and dictionaries mutable because you can change them more easily. You don't have to make copies and tear up memory and do things like that. The penalty is it takes longer to access a list. It takes longer to access a dictionary. You can't go as fast with a list as you can with strings, but they're easier to change, and that's what most people do with coding. So this design using mutable and immutable appears to be a good trade-off between the cost and overhead of new variables, new locations in memory, new stuff versus speed of access. This is not on the exam. This is for your information, because every semester I teach this and somebody wants to know, why would you do this? The answer is because decades of computer science experience says this is a decent trade-off. It gives you good performance and not too much complexity. Okay. How do you tell which is immutable and which is mutable? Immutable, ints, floats, spools, strings. Don't worry about the other stuff. Mutable, list and dictionary. Don't worry about sets. Okay. That's the term, how they can be changed. Now, here is where you might easily run into a problem, and this is what I want to talk about. When you have a parameter, an argument in the main program, a parameter in the function, Python behavior is different depending on whether you're using mutable or immutable functions. So I'm going to define this function that I call strange stuff. And make sure I've got it all copied and not, okay. And now I'm going to have my main program. What did I have? Okay, I'm going to have the list x equals the list 1, 2, 3, and 4. And now I'm going to say y. Let me get my code correctly from the main program. Okay, I'm just going to call my function strange stuff. Let me do this correctly. So let's be consistent with how I am in the slides. Be less confusing for you that way. Okay. I define main list. I've got an indentation error. 1, 2, 3, 4. I call my function, and then I print out the results. Okay, let's run this code. From here on, notice this was my main list. I didn't return anything. The function returned none, right? If there's no return statement in the function, the statement returned none. There's a return of nothing. So how did main list get changed? It obviously got the value 5 appended from the code in the function. Come back up here and fix it. Okay. It obviously got the value 5 appended. And the reason is because this list is a mutable value. It's a mutable variable because it's a complex list. What Python does is when you pass argument, parameter, you get the same location in memory. If you've heard the computer science time call by reference, that's what this is. If I come down here and I run this, and now I say, what is the ID of main list? This is the location. And now what is the ID of a list? The function is ended, it's not defined. Print ID of a list. Okay, now we'll run these two again. That's the ID of a list, and now the ID of main list. And unless I messed up again, what happens is you see that these are the same location in memory. Okay. If what you are passing to the function is a list or a dictionary, they are the same location in memory. You just pass a pointer to that location in memory. Python does. And so you change the value of your list in the main program by what you do in the function. If this is an integer or a string, you do not. Okay. So let's change this so we also passed an integer, num. Let's say num plus equals 1. Let's print the ID of the list. Let's print the ID of num. Now down here, we have main list is 1, 2, 3, 4. Main num equals 2. Call the function with main list and main num. Now let's just print the ID, or print main list and main num, and I'll do the IDs. All right, here we go. Here we go. Okay. So in the function, This is the location in memory of the list parameter. This is the location in memory of the list in the main routine, the main function, the main program. They are the same. For the list, they are the same. For the integer, this is where the main program is. This is where the function is, the function string stuff. These are not the same. So when I changed the value here of the integer, I did not change the value in the main program. When I changed the list in the function, it changed the list in the main program, even though I didn't return anything. The only return statement is still a return none. Okay, it's just this return right here, which returns none. Nothing is returned that changes anything, but Python behaves differently with the argument parameter that are a list. You can change it, and the argument parameter that are an integer, that are an immutable variable, you don't change them. Okay, so that is the difference between passing mutable types to a function and passing immutable types. This will bite you somewhere in a sensitive part all the flipping time. What will happen is you will pass a mutable variable to your function. You will change it in your function, not realizing that you are also changing it in your main program or your calling routine. And then you'll try to figure out where this bug is, and you'll go crazy until you find it. Mutable and immutable variables work differently when you're passing them to the function, because when you're passing the mutable variable as an argument / parameter to a function, you pass a pointer to the same location in memory. It is exactly the same thing, and you will change it all at once. When you pass an immutable value argument parameter to a function, you just pass a copy to a new location in memory. It doesn't change anything. Okay. As I said, why? Mostly because that's the way the guy who originally wrote Python thought it should work, and most users have agreed with him, and this has caught on. It'll drive you crazy. It'll take you a while to debug. It just works that way. Okay. So what do you do if you don't want to change the value of the original list? I don't want to append 5 to 1, 2, 3, 4 in my original list. How do I prevent from doing that? You can make what is called a deep copy. A shallow copy just is a pointer to the original location, and you're working on the same thing. A deep copy gives you a whole new location in memory. Okay, so 2 ways to make a deep copy in a one-dimensional list. You use the slicing. List copy equals main list sub, from beginning to end, or you just use the list constructor function to create a new list. That is what's called a deep copy. That lets you work with a brand new copy of the list, and you will not mess up your original. And that's key. Not messing up. If what you want is to not mess up the original, not change it at all, just work with a temporary copy, then you have to do this deep copy function using either a constructor or a slice. And then they copy the elements into a whole new object, and you don't mess up the original. If it's a list of lists, warning, this by itself is not sufficient. You're going to have to go through the entire thing, the entire 2-dimensional list, 3-dimensional list, and do it piece by piece, or you're just going to mess something up. Okay. In a 2-dimensional list, you get the shallow copy, the multi-dimensional list. It's a truly independent. You have to copy all the components one at a time. Okay. If you have int strings and floats, then shallow and deep copies essentially work the same way. If you have a 2D list, the only way to make a true deep copy of a 2D list is copy every component one by one. Again, I'm out of time because I spent so much time on the project, but I think that was important that we had to spend time on the project. What you need to take away from this lecture, what you're going to be responsible for on the exam, what I want you to learn going forward when you move on through next computer science or whatever classes. Mutable. It can be changed after creation. It can mutate. It can be a new coronavirus. It can be a new list. It can be different. Immutable. It cannot be changed. In Python, simple types like int, strings, etc., are immutable. If you change the value, it means you change the object, you get rid of the old location in memory, you have the new value in a new location in memory, it's a new object, the symbol table entry is different. A mutable object, Python keeps the ID, the pointer to the same location in memory. When you change it, you can change it, life is good. However, that means that if it's a list or a dictionary, you might unintentionally change it. If you are worried about unintentionally changing a list because it's mutable, you have to make a deep copy and you have to work with a deep copy. That is what you need to know for mutability and immutability. The test questions are along the lines of, what are the immutable types you know of right now? Or here's a function, when I call it, this happens. Why did that happen? And the answer is because a list is mutable or a dictionary is mutable. That's what I need you to know. Other than that, please, by Monday, I'm going to check with you. I'm going to ping you. Make sure you've started the project. Make sure you're able to copy that starter file. You can load it. You can work with it. You can see that it does what it's supposed to do. We need to get moving forward because there's a lot of work coming. Okay. Those I gave extensions to for homework. That's due by midnight tonight. Please get that done. And next week we get into recursion, which is another fun topic that everybody either gets intuitively or it drives them nuts. And we want to make sure that even the people who it drives nuts understand it really well. With that, I'm going to stop recording. If you have any questions, I will attempt to answer them. And I will be here for a while. Otherwise, have a good weekend. Get everything done. And I will talk to you next on Monday.